Okay, so the very final syscall that we're going to talk about is the mount syscall. Mount is basically a syscall that allows user to add an extra drive, mounting it to a new place in the directory tree. What what does this mean? So suppose that you basically buy the new latest and greatest USB storage device, maybe 1 terabyte external storage device. You connect it to your computer, and you basically, since we said that Linux has a tree that starts at slash, right? That means that you need somewhere to mount this data, to put this data in. The way that Linux deals with this is basically using the mount command, and this mount can be done either automatically, and most new Linux GUI based Linux versions have that, like Ubuntu for example. When you connect a new drive, using your USB, it will actually detect it and use this command to mount the storage device. So mount minus T, so you're mounting this file system, and you're going to mount it as extended third, which is a type of file system. Um, it, well, you really do not need to know what an extended third is, but you can know the idea is that there are multiple file system implementations, and extended ext3 extended third is one of them. There's ext2 extended second. There's ntfs. There's FAT. There's FAT32. I mean, there are all of these different file system implementations. So you mount your device, which is in that case, as we said, that all devices basically will have a single file that is like their device driver. So in this case, your device is slash dev slash SDA1. This is where your actual device is. So you're going to mount this device into slash home slash users, and then if SDA1, if the file system that you just connected using USB, if the storage device that you connected using USB had two files that are called A and B, then when you ls slash home slash users, you'll find A and B. So this is sort of a way to hook up new storage space into the system. Now that we have talked about the different syscalls for we have talked about mount, we have talked about RM directory, we have talked about unlink, links, we have talked about reads and writes, open and close. I mean, we have basically covered quite a bit of what the file system interface, the file system API looks like. Let us look at how it is actually implemented and basically down below on the block level. So file systems are generally pure software in an operating system. So you basically have it's mostly implemented in software. Although the hard disk can actually dictate some implementation details, the actual physical hardware can have such dictating can dictate some implementation details. Nevertheless, it's mostly software, pure software. A file system is basically is an on-disk data structure that also allows the operating system. This is allows the operating system to open, read, write files. Okay, so it's basically a way to structure the disk to allow us to open, close, read, and write. File systems can get pretty complicated, so we're going to start with one of a very simple example. So suppose that you are building a file system, and you come up and basically say that, okay, I'm going to divide my file system into 4 kilobyte blocks, which is actually a fairly common size for file system blocks. Okay, and these 4 kilobyte blocks, I mean, if you remember, we said that a disk sector can be 512 bytes, so 4 kilobyte blocks is actually four disk sectors. So you have multiple 4 kilobyte blocks, and let us basically talk about small file system with 64 blocks each of them of 4 kilobytes. Okay, so let us ask a question. 64 blocks, each of them having 4 kilobytes. How many bytes is in the file system? And hopefully you said it correctly. You basically multiply 64 multiplied by 4 kilobytes and you get 2 to the power of 18 bytes. Okay, so this is the number of bytes in the file system. As the main aim of having a file system is to actually store data, so you basically have a data region that is comprised or that takes most of the space on the disk, and then you have a metadata region which takes much less space on disk. So let us reserve most of the file system. So basically, with the exception of the first exception of the first 8 blocks, we will reserve everything else to actually be our data region. Okay, where we will store data. Okay, but yet again, we need to store metadata somewhere. So the first 8 blocks, okay, each one of them is again 4 kilobytes, will be used to actually store the metadata. So we will reserve the first 5 blocks for inodes. Okay, so the first 4 kilobytes are for inodes. Inodes do not need the whole block for the metadata for each file. Your inode is basically the data for each file that you have. So the 256 bytes inode is quite common. So 256 bytes is plenty of space to store all the metadata for each file. So for each file, you will store on these inode blocks the first 5 blocks that you have reserved for the last blocks from basically block 3 to block 7 that you have reserved for inodes. You're going to store for 256 bytes for each file. Let us ask ourselves another question. You have 5 blocks for inodes, each one of them having 4 kilobytes. So each block is 4 kilobytes, and each inode requires 256 byte. Okay, so how many files can we have on this file system? Again, I hope you got it right. It's 80 basically. I'm sorry, it's probably disturbing that I had drink while recording the video, but this is the only way I do not lose my voice actually. I need constant supply of warm drinks. So you have 80 files that can be stored on this file system. Okay, now we need to track which inodes and which data blocks are free and /used. Okay, so there's the inode data, and then you basically need somewhere to track a bitmap, to have a bitmap where you basically have for each inode 1 bit that basically says that this inode is empty or this inode is full. Okay, so is this file name, is this low, as we said, each file will have like the names that we give it as humans, like mycv.pdf. Okay, and that mycv.pdf will be basically pointing to an inode number, a lower level number, and you have basically in this file system you can have an inode 0 up to an inode 79. This is basically all the inodes that you have that you can store in this system. So some inodes will be taken, some inodes will not be taken, basically meaning that some files will exist, some inodes have not been linked to any real files, and so you'll use a bitmap to show this. So you'll need 80 bits, basically 0 not taken, 1 for each bit. For each inode you have 1 bit, and if the bit for that inode is 0, that basically means that this inode is not taken. If it's 1, then this inode is taken. Okay. In addition, you now have the constraints on the inodes. You cannot have more than 80 inodes, but also you have constraints on the total amount of data that you can store. So you had 64 blocks of data, you kept 8 for basically metadata. So you only have 56 blocks where you can store data. Each of these blocks is 4 kilobytes. And basically what you want is that you would like to make sure that you know which blocks are being used and which blocks are not being used, so that when a new file, when you're creating a new file, you know which parts of your storage is free, and basically which inodes are free, and then you can basically create the file, allocating to that file some inode. The operating system will do that, and allocating the number of blocks that the file will need, if these number of blocks, if there are enough empty blocks. Okay, so you will have basically 56 bits, because you have the total size of your storage was 64 4 kilobyte chunks. You took 8 out for metadata. Okay, so you're left with only 56 blocks. Okay, so for each block you again have 0 1 bit, 0 not taken, 1 taken. Okay, and of course you can free inodes, but when you delete files you can free bits, you can free blocks, or maybe the file basically stops shrinks. Some files can shrink, you run WinZip or something on that file, or WinRAR or whatever, you compress that file so it takes less, and you free some blocks. So I mean, these blocks, the 56 bits, will change to zeros and ones based on what is actually being used. But let's be lazy and use the whole block for each. And then when mounting a file system, the operating system needs to know which kind of file system is on the disk. For example, how many inodes are there? Is it extended third, extended fourth, extended second? Is it an NTFS file system? Is it a network file system? I mean, whatever the different file systems that you can mount, basically, you need to handle them. So you store this in what we call a superblock. So it is the metadata about the file system itself. It's not just metadata about the files, it's now metadata about the file system itself. So that when you run the mount command, or when you just connect your USB drive, what will happen is that your operating system, Windows or Linux, will read data block 0. And from the 0th block, it will know, okay, this is a file system that looks like this. This is a FAT32. This is an FAT. This is an NTFS file system. This is the maximum number of files that I can have. This is the total size of this file system. So how large it is, and so on. So this is your super block. Sometimes also people call the whole first 8 blocks as the super block. So I mean, there are two naming conventions. One of them is that the superblock is just about the file system, and one of them is that everything, including the inodes, is part of the superblock. Then when you want to find an inode, each inode in the system has a number, as we said. Okay, and these are actually how you identify where a file is. Okay, so if you're looking for inode 32, you need to know that the address on disk is 32 multiplied by the size of inode plus the start of inode region, i.e., so the size of one inode in this case is 4 kilobytes. So you multiply 4 kilobytes multiplied by 12. Okay, multiplied by 32, because you're trying to access the 32nd